Welcome everyone to another educational live stream here. It saddens me to learn that mathematician and genius John Conway, inventor of Game of Life and among other things, unfortunately passed away from this virus thing that we are going through right now. So also recurring theme not to take this analog virus stuff too easy. So Game of Life is a little bit of a homage here. May he rest in peace. And Game of Life, for those who did not know, is a mathematic theoretical algorithm in the range of cellular automation that mimics a little bit the Game of Life, so to say, two-dimensional orthogonal grid of square cells, and these cells are either dead or alive, and here usually seen here in some color here in the visualization, and they populate here in each round depending on the surrounding cells, meaning depending on, you can of course define this, but as defined here in Conway's Game of Life, in 3 or 2, depending on whether it's a live or dead cell, whether this propagates into the next rounds or survives or forms new life in the next generation. In the late 1940s here, John von Neumann created life as a creation, defined life as a creation of being an organism which can reproduce itself and simulate in a Turing machine. And then later here, this, motivated by this question, mathematical logic, simulates a game. Among others, John Conway began doing experiments in 1968, variety of different 2D cellular automation rules. And certainly really interesting. Here are some patterns. So depending on this, whether it's a live or dead cell, 2 or 3 patterns, there are surprising patterns forming here from the cellular automation. And you can, so not only is it interesting that there are some static live patterns that remain the same in each generation, also some oscillating here with a period of 2 or 3, or really interesting thing, and some are moving here, like glider pattern, lightweight spaceship and stuff. And this creates surprisingly interesting patterns. So like here, this single Gosper glider gun creating gliders. So really interesting kind of animations here. And being here an educational channel, I spent here an hour or 2 implementing this here in RISCV. And so this is running on our FPGA, and I can show you the source code in a second. Of course, the source code, many examples out there here on the ULX3S. And as you see here, when you compare this to this Wikipedia pattern, this is exactly this pattern, and really interesting that this simple Game of Life with this simple set of rules can form this kind of nice, oops, also wrong camera, can form this kind of nice animations. What can it be used? Well, not only in terms of teaching and simulating life, but certainly also generating patterns in game logic and other things like that. Or, for example, previous shout out here in terms of mathematically knit scarf, shout out here of previous year that I supported this knit jack here from Fabrian FBZ here on Kickstarter, or no, if you're interested in this. So not only can you do game logic and other interesting patterns, but also so much to this little promotion. But if you go out, certainly probably want to keep yourself a little bit covered. So nice patterns, not only for your knitting stuff, but game logic and animations. So as these rules here are relatively simple, also too many camera views, right? Can never have enough of those. So the simple rules, the only additional thing is I color this nicely. Of course, in my first prototype, I had this static gray that didn't look as nice. I thought for this YouTube, a little bit of 5 minutes extra effort of coloring it randomly so that it looks a little bit nicer. So this is exactly this pattern. And implementation, of course, pretty simple. If we take a look here in our code, so this is the same RISC-V firmware as per the previous videos running here on this ULX3S board. And also I changed the camera setup here. Hope this is a little bit better for the future. And so yeah, ULX3S, previous videos, FPGA, RISC-V Pico, RV32, and here our firmware where we have all the previous videos, VGA, MIDI fun. And so yesterday, still rocking here the MT32, today Game of Life. And let's see how many lines are this. So for this starting, this is not the promised programming 101, although a little bit basic. So let's quickly go over it. We define here some const unsigned integer 8-bit because we don't need more. The width and height, we run this in text mode. Here for us, it might not look like text mode, but this is, you could do this exactly the same on a PC. It's all, actually it's not, our text mode is slightly fancier. We have 30 rows, so this is 80 by 30, regular VGA is 80 by 25. So we have a little bit more room for animation. This is because we run this at 480 by 480, 460, 480 by 640 by 600, it's not my day, probably 640 by 480 divided by 16 and 8 for the text pattern grid, and to have here square pixels I use double text characters to have here square pixels, so for this to look a little bit nicer. So otherwise you could nearly do this on a VGA. Maybe there is a 30 row text mode, not sure, but maybe not. This is later, this is just some initialization fun here for this patterns here. As you see, we have here this kind of initialization tiles. Of course, you can initialize this randomly or with whatever, but you can also initialize this with this known patterns. And that is what I later had here. Of course, initially I didn't start with this. Initially, I just started with this drawing and generation. So how does drawing work? So we just take some memory somewhere, doesn't really matter much, in the size of 40 by 30. This is the size of our live set here. And also I can move this a little bit. Where's my trackball? Also 0 frames, so far so good. So of course, how did I start? I just took some memory. We run without an operating system anyway, so just grab some memory and initialize and draw it. So drawing, again, text mode. This color is just a later addition. Initially I just had gray, but otherwise this is our state, just somewhere in memory. State as in 8-bit per live or dead cell. And then for all y to live height and x to live width, this multiplied by 2 is only for doubling this character in text mode for square pixels. And then set here our VRAM. This is our pointer to video memory as per the previous videos. And multiplied by 128, this is our current width. This is wider than 80. Maybe I change this later, but right now this is for simple Verilog logic here for the text mode output. In a PC you would have here multiplied by 80. And so we initialize here two advanced text mode cells, x and x plus 1, because we want to have square pixels in text mode. And then whether the state is alive or not, we initialize this here with a color. Initially I had here gray, as I said, but now, so gray would just be like F or whatever color you want to use. And Otherwise, what I've done here now, I use a color here, initialize it with 1 because we don't want to have black. Black would be 0. And then if the color becomes too large, then we reset it to 1 again for the next round. So this is drawing super simple. This is just some initialization of blocks. This was my initial code for initialization, just setting some pixels with some helper functions here. Live set depending on whether it's out of bounds in our C array of memory. If it's out of bounds, then nothing, which by the way we could also simplify now that I changed this slightly, just because why not, to keep this code most readable. And later, so my initial live seeding function here is of seeding some initial state, because if it's totally black or white, certainly not that interesting. As you see, initially I had here this live block glider blinker block blinker glider patterns here for testing. Later I made this slightly more sophisticated, but more to this in a second. I have, you know, some fancy array initialization. But the evolve function here for each live generation, going here through all our game of live state, basically again y to live height and x to live width, and counting here the surrounding population count. Initially I had this open coded, but this became too error prone, so I have, you know, some fancy helper function. And of course you could optimize this further, or actually maybe the compiler actually optimizes this, because this is also the benefit of not doing this in assembler but having a freaking compiler, because for sure the compiler inlines. This inlining means this live add. We can also write here inline, but I'm sure GCC or G++ is intelligent enough to inline this. This means that hopefully we could check the assembly, but I'm pretty sure GCC should optimize many of these out-of-bound comparisons here away, at least I would hope so. And then depending on the population count here, based on this Conway's algorithm for game of life, we decide, where was it, even somewhere in the beginning, so any live cell fewer than 2 live neighbors dies as an underpopulation. Live cells with 2 or 3 live neighbors live on in the next generation, and live more than 3 live neighbors die as an overpopulation. These rules can be condensed to any live cell with 2 or 3 live neighbors survive. Also here, simplifying logic assignments, right? This can, by the way, I think this can be further simplified, because they have here condensed down to live cells 2 or 3 neighbors, as well as dead cells with 3. So this further optimization could be probably slightly higher performance. As you see, any cell with 3 live neighbors becomes a live cell, so most likely we can further optimize this to first checking if the population count is 3, and only then additionally check whether it is a dead cell for this differentiation, but whatever. So then, as I said, whether it's a dead or a live cell, so the new state, we have here 2 sets of state. We have the old state that we cannot runtime modify, because we still count in the population count as we iterate over that. So this is why we have here 2 states, calling this live evolve function with state, with the current state and the new state, and setting this new state just a pointer here, iterating over it, tiny little optimization. Otherwise we would need to multiply here. You could of course multiply y by width plus x, but just linear optimization, iterating over there, setting this new state. And here's our who. So you see how long is this, just a couple of maybe 80 lines of code or something, not really much in our RISC-V firmware. What do we do here in the whole game of life? We declare some state. We just basically grab here our pointer to SDRAM, here as in SDRAM there, SDRAM controller, previous video. Actually our built-in SRAM should be slightly faster, but I wanted to stress test our SDRAM, because why not? Can never test enough. So live seed. So we have here 2 states, again pointer to SDRAM, and the second one is just pointer to SDRAM and then another game of life further. this means live width by height. We have here 64 whopping megabytes, so doesn't really, of course in a real operating system we should malloc this, so probably want to share, like, and subscribe for malloc memory management here in our bare metal RISC-V firmware and microkernel operating system to come. Then we seed this, because when we power this on, this is random initialized garbage. So initialize this, memset, put there some nice pattern, and then draw it. Initially for testing I had to get character, but of course I have commented this out. Then for 666,667 iterations, or if we have here a character on the UART, kind of nearly infinite loop over this. Again, seed, draw, and then evolve from the state to the new state, draw this new state, and then we could have, this is a little bit of keeping it stupid simple, we could have two pointers, we could swap the pointers, or we can just evolve this. So because what does it mean? We have an old state and a new state. The next time we would need to do this. Actually, we could also implement, yeah, but actually swapping, yeah, whatever. We could also exchange the pointers here, but yeah. Just do this again, evolve with the second state and the old state and draw it again, and has the added benefit of not checking the serial line too often. And with this simple code, it worked relatively straightforward. I only had a typo in ironically the height. I typed here 60 for some bizarre reason. And of course I had here some typos. I typed in here this graphic from Wikipedia here, counting those pixels, or either there or here. I think I counted the pixel in this graphic. I had there some typos obviously in there. And how this works is I have here a pair of uints for this more fancy initialization, and typed in here all the pixels, so you can count of this. So 0, 1, and 0, 1, 2, 3, 4, 5. And then I have pairs of pixels to initialize here, 1, 5, 2, 5, 1, 6, 2, 6, and so on. So basically just counting through all this graphic here of Gosper glider gun. And as you see, the result here relatively impressive in my opinion. Certainly this kind of nice game demo graphics that you can impress people with. It's running, so this is running at full speed. So yes, you can see our 40 MHz RISC-V CPU, not the fastest, the RISC-V, the Pico RV32, it's not pipelined. So only, I think, probably one instruction at a maximum rate of 4 clock cycles, plus our SDRAM controller, relatively slow. Previous video also, it's already bursting for converting this 16-bit SDRAM to a 32-bit, and the whole state machine of SDRAM programming, of generating the address, takes nearly, or the whole state machine takes 16 clock cycles, plus it's however running double the clock rate, so we run 41 megahertz. So this is the SDRAM controller is running this twice the clock speed of 84 megahertz or 83 something. And thankfully I implemented bursting, meaning with one address generation in the 16 state machine we get two 16-bit words out of there, so that we only have to wait approximately 14 clock cycles with twice the like basically double data rate compared to our RISC-V. So this is a double data rate 14, so it's like 7 clock cycles to read. And yesterday, just for the pure fun of it, I optimized writes, so that because writes are slightly faster, I could optimize writes slightly further by buffering it completely. But for now, I made it like 1 clock cycle faster, so writing yesterday, just because why not. But yeah, of course the internal SRAM in the FPGA would be faster. It's 1 cycle, so yeah, probably 4 times slower than it should be, but at least yeah. The animation speed is just right to look nice, but this is of course not the totally most impressive for 40 MHz RISC-V. But Yeah, how could we get this faster? Well, we could this faster by implementing, certainly there are two low-hanging. For the future, if you want to share, like, and subscribe for this kind of hardware and software fun, certainly one thing is implementing or reusing someone else's Claire's Pico RISC-V of Pico, as in keeping it most stupid simple for educational purposes and debug and formal verification goodness. So pipelining RISC-V certainly easily 4 times faster, and then of course caching and more caching with a simple cache here for the SRAM infrastructure, like 1 cycle cache in the SRAM, certainly would speed this stuff up by easily another factor of 4. So most likely we could easily get this 16 times faster, but that is not the point of this video. This video was to pay homage. May he rest in peace, John Conway. And this kind of things, in my opinion, what many people should probably know, and too few people know also, Donald Knuth, have your local library, read some books, especially in this day and age when you need to stay at home. Do fun stuff at home, like educational fun hobby projects like ours here, of having fun with good old-fashioned, also wrong camera, having fun with good old-fashioned MIDI devices here, Roland MT32, MIDI goodness, FPGA, do hardware, software, educate yourself, read some books that you were looking to read for quite some time, Donald Knuth or other Conway theoretical informatics stuff. And in my opinion, this is what a lot of people, especially people who just get into web development and think just randomly trial and erroring with HTML code, that is computer science. Unfortunately, I have to break you the news. No, it isn't. In my opinion, many more people should read some good old computer science, theoretical algorithm and stuff. Probably the computer science world would be a better place with less peak bugs and better working hardware and software if more people would read more theory. Yeah, basically that's it, what I have for you today here in this educational RISC-V series. I hope you enjoy this fun we have with our RISC-V FPGA hardware, software, Linux and open source uses, and how easily you can write basic animation algorithms. Next, probably we could do this in graphic mode, but probably I knew already the performance of this. This is also knowing the performance of your hardware and software. It's not pipelined, it's not cached, so yeah. So certainly not writing all the pixels, although we have graphic mode, but yeah, certainly quite some stuff still to do. Also here on the hardware front, I was thinking for graphic mode, because this is right now text mode, misusing text mode, I was thinking maybe I implement also any power of 2 pixel scaling, so that we could switch to graphic mode just for the fun of it, or even easier or more straightforward programming, and basically implement pixel doubling, quadrupling, so like any power of 2 integer scaling support in the video core, because our own video core, right, previous videos. And certainly also I was thinking maybe also for better animation, because next certainly games with audio and video stuff also support adjusting the frame buffer base address. Then we could have hardware scrolling in text and graphic mode, and also double buffering, dual frames in graphic memory. So, but this is actually pretty easy. Just have one control register that determines the start in video VRAM, and this also means most likely changing the text mode. As I said, right now it has 128 character width, which is of course quite wasteful just for the easier hardware implementation, but it's actually not too more difficult to just count this linearly. Right now I'm dividing this by actually shifting this by the shift amount of 128 equivalent, but we can just linearly count this and have a better hardware scrolling text mode so that we can have this really 80 character cells by 16-bit for color and text glyph, and actually make better use of this, because right now a lot of is here actually wasted. Here wasted of 80 to 120 for no good reason. And so yeah, implement this start of frame buffer with 80 characters. But yeah, there's always something you can make better in your hardware and software. I hope you learned something, and yeah, don't forget to share, like, and subscribe for all the updates to come, and stay safe. Take your precautions in your self-isolation probably, and go out with mask and stuff. Hope to see you soon for all the next videos and live streams to come.